We are starting the connection with Cambridge. Apparently it should work okay. There will be an image of Stephen on one of the sides, and the other one will be the projection of the PowerPoint. Well, Stephen was thinking to come to the meeting. We attempted for almost 1 month because he cannot travel by plane, and he was looking a way to reach Rome by train. Any one of you who has been coming on the railway in Europe understand the difficulty of connecting at the border, and for a while he was optimistic to come through the Gotthard and then from Nice, but finally he was, with this heat, a good idea to use the electronic means directly from Cambridge. I understand he will talk about black holes and the quantum black holes. This brings us back to 1972, when we were in Les Houches, and there was the major interaction of understanding the mass formula, and there was practically a split into two completely different directions. One direction was the one toward the macroscopic black holes, solar mass black holes, all the way up to 10 to the 8 or 10 to the 9 solar mass black hole. This was one direction. And the other one was for which, of course, you have no need of quantizing gravity, but you consider classical gravity eventually with a quantum effect on a classical background. And then instead the adventure to try to quantize to quantum a black hole very tiny in size, in which the horizon is of the order of the Planck length, or anyway much smaller black holes with respect to the astrophysical one. And I look for, this was the moment in which Jacob Bekenstein was a student still of John Wheeler at Princeton, and as you will see also in the exposition at the Bezos Foundation, that we came out with the mass formula with Dimitris Christodoulou. Okay, I think Stephen will go back to some of this in his lecture, and I ask the Regia to go on with the images.
The energy released will create sufficient pressure to support the star against its own gravity, giving rise to an object with a radius about 5 times the radius of the Sun. The escape velocity from the surface of such a star would be about 1,000 kilometers per second. That is to say, an object fired vertically upward from the surface of the star, with a velocity of less than 1,000 kilometers per second, would be dragged back by the gravitational field of the star, and would return to the surface. Whereas an object with a velocity greater than that would escape to infinity. When the star had exhausted its nuclear fuel, there would be nothing to maintain the outward pressure, and the star would begin to collapse because of its own gravity. As the star shrank, the gravitational field at the surface would become stronger, and the escape velocity would increase. By the time the radius had gone up to 30 kilometers, the escape velocity would have increased to 300,000 kilometers per second, the velocity of light. After that time, any light emitted from the star would not be able to escape to infinity, but would be dragged back by the gravitational field. According to the special theory of relativity, nothing can travel faster than light, so that if light cannot escape, nothing else can either. The result would be a black hole, a region of space-time from which it is not possible to escape to infinity. The boundary of the black hole is called the event horizon. It corresponds to a wavefront of light from the star that just fails to escape to infinity, but remains at the Schwarzschild radius, 2gm over c squared, where g is Newton's constant of gravity, m is the mass of the star, and c is the velocity of light. For a star of about 10 solar masses, the Schwarzschild radius is about 30 kilometers. There is now fairly good observational evidence to suggest that black holes of about this size exist in double star systems, such as the X-ray source known as Cygnus X1. The X-rays are given off by matter falling into the black hole. There is also a massive black hole 4.31 million times the mass of the Sun at the center of our galaxy. There might also be quite a number of very much smaller black holes scattered around the universe, formed not by the collapse of stars, but by the collapse of highly compressed regions in the hot dense medium, that are believed to have existed shortly after the Big Bang, in which the universe originated. Such primordial black holes are of greatest interest for the quantum effects I showed It suggested something dark and mysterious, but the French, being French, saw a more risky meaning. For years, they resisted the name True Noir, claiming it was succeed. But that was a bit like trying to stand against the weekend, another Frank Lee. In the end, they had to give in. Who can resist a name that is such a winner? From the outside, you can't tell what is inside a flagpole. You can throw television sets, diamond rings, or your worst enemies into a flagpole, and all the flagpole will remember is a total mass and the state of rotation. John Wheeler called this a flagpole has no hair. To the French, this just confirmed their suspicions. A flagpole has a boundary called the event horizon. It is where gravity is just strong enough to grab light back and prevent it escaping. Because nothing can travel faster than light, everything else will get dragged back also. Falling through the event horizon is a bit like going over Niagara Falls in a canoe. If you are above the falls, you can get away if you paddle fast enough, but once you are over the edge, you are lost. There is no way back. As you get near the falls, the current gets faster. This means it pulls harder on the front of the canoe than the back. There's a danger that the canoe will be pulled apart. It is the same with flagpoles. If you fall towards a flagpole feet first, gravity will pull harder on your feet and your head, because they are near the flagpole. The result is, you will be stretched out longwise and squashed in sideways. If the flagpole has a mass of a few times our sun, you will be torn apart and made into spaghetti before you reach the horizon. However, if you fell into a much larger flagpole with a mass of a million times the sun, you would reach the horizon without difficulty. So, if you want to explore the inside of a flagpole, choose a big one. There is a flagpole of about 4 million solar masses at the center of our Milky Way galaxy. Although you wouldn't notice anything particular as you fell into a flagpole, someone watching you from a distance would never see you cross the event horizon. Instead, you would appear to slow down and hover just outside. You would get dimmer and dimmer and redder until you were effectively lost from sight. As far as the outside world is concerned, you would be lost forever. The first hint that there might be a connection between flagpoles and thermodynamics, the science of heat, came with the discovery that the surface area of the event horizon, the boundary of These properties suggest that there is a resemblance between the area of the event horizon of a black hole and the concept of entropy in thermodynamics. Entropy can be regarded as a measure of the disorder of a system, or equivalently, as a lack of knowledge of its precise state. The famous second law of thermodynamics says that entropy always increases with time. There is an analogy between the properties of black holes and the laws of thermodynamics. The first law of thermodynamics says that a small change in the entropy of a system is accompanied by a proportional change in the energy of the system. The fact of proportionality is called the temperature of the system. There is a similar law relating the change in mass of a black hole to a change in the area of the event horizon. Here, the factor of proportionality involves a quantity called the surface gravity, which is a measure of the strength of the gravitational field at the event horizon. If one accepts that the area of the event horizon is analogous to entropy, then it would seem that the surface gravity is analogous to temperature. Although there is clearly a similarity between entropy and the area of the event horizon, it was not obvious to us how the area could be identified as the entropy of a black hole. What would be meant by the entropy of a black hole? The crucial suggestion was made by Jacob Wittgenstein. It goes like this. When a black hole is created by gravitational collapse, it rapidly settles down to a stationary state that is characterized by only three parameters: the mass, the angular momentum, and the electric charge. Apart from these three properties, the black hole preserves no other details of the object that collapsed. This is the no-there theorem. The no-there theorem implies that a large amount of information is lost in a gravitational collapse. For example, the final black hole state is independent of whether the body that collapsed was composed of matter or antimatter, and whether it was spherical or highly irregular in shape. In other words, a black hole of a given mass, angular momentum, and electric charge could have been formed by the collapse of any one of a large number of different configurations of matter. Indeed, if quantum effects are neglected, the number of configurations would be infinite, since the black hole could have been formed by the collapse of a cloud of an indefinitely large number of particles of indefinitely low mass. The uncertainty principle of quantum mechanics implies, however, that a particle of mass m behaves like a wave of wavelength h over mc, where h is Planck's constant and c is the velocity of light. In order for a cloud of particles to be able to collapse to form a black hole, it would seem necessary for this wavelength to be smaller than the size of the black hole that would be formed. It therefore appears that the number of configurations Wittgenstein suggested that one could interpret the logarithm of this number as the entropy of the black hole. The logarithm of the number would be a measure of the amount of information that was irretrievably lost during the collapse through the event horizon when the black hole was created. The apparently fatal flaw in Wittgenstein's suggestion was that if a black hole has a finite entropy that is proportional to the area of its event horizon, it also ought to have a finite temperature, which would be proportional to its surface gravity. This would imply that a black hole could be in equilibrium with thermal radiation at some temperature other than zero. Yet according to classical even in a power station, because it would drop through the floor and end up at the center of the Earth. About the only way would be to have a black hole in orbit around the Earth. People have searched for many black holes of this mass, but have so far not found any. This is a pity, because if they had, I would have got a Nobel Prize. Another possibility, however, is that we might be able to create micro black holes in the extra dimensions of space-time. According to some theories, the universe we experience is just a 4-dimensional surface in a 10 or 11-dimensional space. We wouldn't see these extra dimensions because light wouldn't propagate through them, but only through the 4 dimensions of our universe. Gravity, however, would affect the extra dimensions and would be much stronger than in our universe. This would make it much easier to form a little black hole in the extra dimensions. It might be possible to observe this at the LHC, the Large Hadron Collider, at Surrey, in Switzerland. This consists of a circular tunnel, 27 kilometers long. 2 beams of particles travel around this tunnel in opposite directions, and are made to collide. Some of the collisions might create micro black holes. These would radiate particles in a pattern that would be easy to recognize. So, I might get a Nobel Prize, after all. As particles escape from a black hole, the hole will lose mass and shrink. This will increase the rate of emission of particles. Eventually, the black hole will lose all its mass and disappear. What then happens to all the particles and unlucky astronauts that fell into the black hole? They can't just reemerge when the black hole disappears. The particles that come out of a black hole seem to be completely random and to bear no relation to what fell in. It appears that the information about what fell in is lost, apart from the total amount of mass and the amount of rotation. But if information is lost, this raises a serious problem that strikes at the heart of our understanding of science. For more than 200 years, we have believed in scientific determinism. That is, that the laws of science determine the evolution of the universe. This was formulated by Laplace as, if we know the state of the universe at one time, the laws of science will determine it at all future and past times. Napoleon is said to have asked Laplace how God fitted into the positions, the less accurately you can know the speeds, and vice versa. In other words, you can't know both the positions and the speeds accurately. How then can you predict the future accurately? The answer is that although one can't predict the positions and speeds separately, one can predict what is called the quantum state. This is something from which both positions and speeds can be calculated to a certain degree of accuracy. We will still expect the universe to be deterministic, in the sense that if we knew the quantum state of the universe at one time, the laws of science should enable us to predict it at any other time. It was therefore very important to determine whether information really was lost in black holes, or whether in principle it could be recovered. Many people felt that information should not be lost, but no one could suggest a mechanism by which it could be preserved. The arguments went on for years. Finally, I found what I think is the answer. It depends on the idea of Richard Feynman that there isn't a single history, but many different possible histories, each with their own probability. In this case, there are two kinds of history. In one, there is a black hole into which particles can fall, but in the other kind, there is no black hole. The point is that from the outside, one can't be certain whether there is a black hole or not. So there is always a chance that there isn't a black hole. This possibility is enough to preserve the information, but the information is not returned in a very useful form. It is like burning an encyclopedia. Information is not lost if you keep all the smoke and ashes, but it is difficult to read. If Gordon and I had a bet with John Briscoe, that information would be lost in black holes. When I discovered how information could be preserved, I conceded the bet. I gave John Briscoe an encyclopedia. Maybe I should have just given him the ashes. Thank you very much.
Stephen, we thank you very, very much for this very nice presentation and all your effort to be with more than 1,000 participants at Marcel Grossman. You are one of the founders of the Marcel Grossman meeting, and therefore you are still in the International Organizing Committee very active, and your presence today is a beautiful contribution. Thank you very, very much.